All right, so welcome back. We're going to finish 4.1 here. The first thing we're going to look at is how do you convert between degrees and radians. This should be fairly straightforward and simple. We know that 2 pi is equal to 360. And then therefore we can say that 1 pi is equal to 180. So we know that conversion, right? It's like saying if I know that there's 12 inches in 1 foot, I can easily convert from inches to feet or feet to inches. It's the same exact thing, okay? So we just use our two little conversions here, which is basically the same thing. We just want to keep in mind that whatever we have, so 135 degrees, and we can make it over 1 if that helps you, but you definitely don't have to. And I'm going to multiply it. Because I want degrees to cancel, right? I want this to be radians, so I want the degree to cancel. I'm going to make sure that I have my degree on the bottom so that those guys can cancel. And I know that 180 degrees is the same thing as pi radians. So my degrees cancels. And I can just multiply straight across. So 135 pi over 180. And since I want exact here, I'm just going to take my 135 over 180 and I'm going to reduce that fraction. And since I already know what it is, okay, that reduces to 3. The pi is still going to be there, and then the bottom becomes 4. So 135 degrees is the same thing as 3 pi over 4 radians. I want you to try the other two, and then when you're ready to check your work, go ahead and hit play. All right, so check your work here. For B, you should have gotten 3 pi, and for C, you should have gotten negative 3 pi over 2. So hopefully nothing too crazy there. If we look at example 4, it's the same thing. We're just going the other way. So now, since I have my radians on top or my pi on top, and I want the pi to cancel, I need to make sure that I have pi on bottom. And I know that pi and 180 degrees are the same thing. So this becomes, the pi's cancel, and I get negative 180 over 4, which is equal to negative 45 degrees. And that's it. So the pi's should cancel because you have one on top and one on bottom. Go ahead and try the other two, and then when you're ready to check your work, hit play. Okay, so for B, even though it doesn't have a pi, it's still radians, so the pi still needs to go on bottom. And then I just did this in my calculator. 360 degrees divided by pi was about 114.59 degrees. And then C, same thing, the pi's will cancel, and you should get 810 degrees there. So hopefully that's nothing too crazy. If you need help on that, make sure you reach out and let me know. But let's move on and look at how do we find the arc length of things. All right, so here we have arc length. Remember that arc length, if I have a circle, right, with radius, whatever, and I have this angle is theta, my arc length is from here to here. That's my S. Right there. And even though it's curved, right, it's how long it would be if you flattened it out and straightened it out. And remember that we used that equation last time that theta was equal to the arc length divided by the radius. Well, this is just the same equation. All I've done is I've multiplied by the radius on both sides. So I get r times the radius equals the arc length. So it's the same equation as the one that we used previously in this section, just modified it a little bit. So let's look at example 5 here. It says a circle has radius of 4 inches, so my r is 4. And it wants me to find the length of the arc if theta is 240 degrees. Okay, now this is key right here. Theta has to be measured in radians when we're using this equation. So even though this seems like it should be really easy, right? S is equal to r times theta. The only thing is that I have to convert theta from degrees to radians. Should be super simple, right? We just did it. I can make this a fraction. I want my degrees on the bottom, which gives me pi on the top. Degrees can cancel. I get 240 pi over 180, which is 4 pi over 3. So that is my theta right there. So now I can actually solve this where my radius is 4 and I'm multiplying it by my theta, which is 4 pi over 3. Right? How do we multiply fractions? We multiply straight across. So this is 4 over 1 times 4 pi over 3, which gets me 16 pi over 3. And it probably wants my answer in inches since that's my unit, so I can enter this into my calculator, and I get about 16.755 inches. So that is how long the crust of that pizza is, right? Piece of pizza, that's how long the crust is. So just the key here is just making sure that we always use our theta in radians and not in degrees. Okay, let's move on. Same thing, find the length of an arc on circle of radius r, when we're given the radius, intercepted by the central angle theta. So I want you to try these two. Exactly what we just did, making sure that we are using our theta in radians and not degrees. So I want you to try A, B, and C, and then when you're ready to go over it, go ahead and hit play and we'll go through it. Okay, so check your work here. It's the same thing that we just did. If you need to pause the video to check it, that's fine. C was just the same thing. The only difference was is in word problem form. But for all of these, you just have to make sure that you change your degrees to radians. So 45 degrees was pi over 4. 300 degrees was 5 pi over 3. And 60 degrees was pi over 3. And then that should be pretty quick in solving that. The last thing we're going to do, we're going to skip linear and angular speed. The last thing that we are going to do is, oh, I'm sorry, we're not skipping linear and angular speed. My bad. So we're going to do those, and then we're going to go ahead and semi-fill out a unit circle. Okay, so let's look at linear and angular speed. What this is if I have, let's say, a wheel. Here's my wheel. Some sort of wheel, who knows? Okay, and you guys know that I'm not here for my artistic ability. Let's say I have a point on the wheel. And this wheel is spinning, right? Well, as this wheel spins, this point spins at a certain speed. That is its linear speed. How quickly does it take for this point to go all the way around and get back there? Okay? And to find the linear speed, it's S is the arc length, right? How long do you want it to go, right? In this case, I just said how long does it take to go all the way around, in which case the arc length would be 2 pi. But what if I just wanted to know how long it takes to go from here to here? Then I would have to just know that arc length, okay? And T, obviously, is time. Okay. The other type of speed that we're going to look at is angular speed. And this is if I have an angle, how fast is that angle moving as the tire moves or as the wheel moves, okay? So again, S is arc length, and then theta is going to be the angle, and it has to be in radians, okay? So we're basically using this S equals R times theta. So what this comes down to is like, okay, there's a lot of equations going on right here. It's really not that bad, and I do think that sometimes the visual really helps. So we're going to look at example 6, and then you guys will try one. And I'm going to try to draw a circle, okay? And we're looking at a second hand of a clock. So here's the second hand, and it's 10.2 centimeters, okay? So that is the radius of the clock. It says find the linear speed of the tip of the second hand. So how long is it taking it to go 1 second? What's the speed that it goes from 1 second to the next second? So what we're going to do, since we want linear speed, we're going to use this S over T. Okay. Where S, woohoo, right here, is really R times theta, which we just did on the previous problems, okay? Well, I know that the radius of the clock is 10.2. And I know that this second hand goes all the way around. I know that the second hand can go all the way around the clock. And then the question is, how long does it take for the second hand to go all the way around? And I know that it takes 60 seconds, right? That's the time. Could I have done pi in 30 seconds? Sure, right? I know it takes 30 seconds to go from the 12 to the 6 or whatever, okay? And I'm just going to solve this. And I can just multiply 10.2 times 2 pi divided by 60 is about 1.068 centimeters per second is how long each tick mark, or each time that second hand moves, it takes 1.068 centimeters per second. So it goes 1.068 centimeters every time it moves. Okay, I want you to try the next one, the U try. I'm going to leave this up so you can look at this as an example, but it's pretty much identical. You just have a different radius. So go ahead and try the U try, and then when you're ready, you can go ahead and hit play. All right, so check your work here. It should be very similar to the previous one we did. The only difference is now the radius is 8 centimeters. So now every second, this second hand only moves 0.836 centimeters. And that kind of makes sense. If we have a super big clock, right, and here's my second hand, the distance it goes to the next second on a really big clock is going to be bigger than if I have a small clock with the second hand and the distance it goes to the next second. So it makes sense that if the radius was 10.2 centimeters, that it would move further every second than if the radius was only 8 centimeters. It would move not as far every single second. Okay, so let's move on to number 7, where we're talking about angular speed. So how fast basically is like the middle going? Let me scroll down. So I have a car tire here, and it says a 15-inch diameter tire on a car makes 9.3 revolutions per second. That means it spins around 9.3 times every second. Find the angular speed of the tire in radians per second. So that's going to be really, really, really important, radians per second. So the angular speed formula from up above is theta over time. Cool? Okay. Theta is how many revolutions per second I'm going. So I know that there's 9.3 revs per 1 second. They told me that. But I want this in radians per second. So I need to change revolutions to radians. So I'm going to do unit conversion. Remember, whatever's on the top has to go on the bottom. And I want it to be in radians. Okay? So I need to think of a conversion of a revolution and radians. How can I convert that? Well, I know that one revolution, right? If I spin the tire once all the way around, how many radians is that? Should be 2 pi, right? I'm spinning all the way around one time. So my revolutions can cancel, and I'm just going to multiply this across. 9.3 times 2. I'm just going to go ahead and leave it in terms of pi, so 18.6 pi. And then I'm left with radians per second. And that's it. Because of this conversion right here that I can figure out, right? I know that one revolution, one time all the way around, is equal to 2 pi radians. And then now it says find the linear speed of the car. So that's my s over t, right? And remember that s is really r times theta over t. Well, I just found, first of all, r is 7.5, right? This is 15-inch diameter. So the radius is 7.5 inches. I just found that theta is 18.6 pi. And I know that it goes 18.6 pi in 1 second. Right here, because that's what it tells me. 18.6 pi in 1 second. And I multiply this into my calculator, and I get 438.25 inches per second is how fast the car is going. Could I figure that out in miles per hour? Sure. It would probably give me a better idea of how fast the car is actually going. But here in this case, it doesn't ask me to find miles per hour, so I'm just going to leave it in inches per second. Okay, I'm going to leave this up. I want you guys to try it. Remember that this is a key part right here, is knowing that one revolution around is 2 pi radians. Go ahead and see if you can figure this out for the circular blade on a saw, and then we're almost done. Okay, so let's look at this. Circular blade on a saw rotates at 2,400 revolutions per 1 minute. That's given to me. Find the angular speed of the blade in radians per second. Okay, so I need, instead of revolutions, I need radians. So revolutions and radians, right? Since revolutions is on top, it has to be on bottom here. Now I know that one revolution is 2 pi radians. So boom, boom. Now I have radians per minute. But I don't want radians per minute, I want radians per second. So I need to convert again. Minutes here is on the bottom, so in this case it's going to be on top, and seconds is what I want. Then I say, what's the conversion between minutes and seconds? And I know that 60 seconds is 1 minute. So now I can cancel just the minute, and I'm left with radians on top and seconds on bottom, which is exactly what I want. So I'm going to multiply this straight across, and I get 4,000 pi radians on top and 60 seconds on bottom. And if I divide this, and I would leave it in terms of pi, I'm going to get 80 pi radians per second. Hopefully we got that one and feel good about it. Now I want the linear speed of the blade. How fast, right, is a point on the blade moving? And I know that the radius is 4 inches. So remember that linear speed is s over t, but s is really r times theta. Well, in this case, I know that my radius is 4 inches. I know that my theta is 80 pi. It goes 80 pi radians in 1 second. This blade is moving. So I multiply 4 times 80 is 3,200. Excuse me, pi inches per 1 second. And I guess we would just leave that, right? It's in inches per second. So let's go ahead and multiply the pi. And I get 1,000, too many zeros. 1,005.31 inches per second is how fast that blade is moving. Okay, so hopefully you feel good again. If you ever don't feel good about anything, make sure you reach out. Last thing we're going to do is here's what we call a blank unit circle. It says the figure below illustrates angles that you will frequently use in trigonometry. Label each angle with its degree and radian measure. So what I want you to do is I want you to try to do this on your own. If you mess up, it's no big deal. You can always erase it and fix it. I want you to try to do this on your own. And then when you're ready to check your work, you can go ahead and hit play and I'll have all of the answers up here for you. All right, guys, so here is the unit circle filled out. I went through first and I did all of the degrees because those were ones that I knew that I could easily find. And then I went through and started filling in the radians that I knew and then using information from that to start filling in the ones that I didn't know. So again, make sure you have this filled in. We will fill in plenty of unit circles again. And so there's going to be plenty of time to learn the unit circles, so don't stress about that. But now would be the time to start really making sure that you're knowing it. I would say at least the first quadrant 1 of degrees and radians at this point. As always, reach out if you need any help, and I'll see you soon.